Hi, Ujwal. How are you?
I'm very good, thanks. I haven't slept, so let's see what happens.
So maybe in the meantime, let's play some music. I'm sorry that you were not able to sleep.
No worries, no worries. Let's see how it goes.
Hey Cecile, how you doing?
Hello.
Hi, Abyss. Yeah, I was playing some music because if we're too silent, some people might think that there is something wrong with the room. So I'm very thankful that you're here. And yeah, I would like to introduce you to Ujwal. Abyss here is a neuroscientist and is also recently been doing AI. And he missed the previous room that you had the Ujwal. So it's good, that you're able to make it. And Abyss, Ujwal did not sleep because he is based in Germany. And he has to catch up with the day schedule. So we are very thankful to him who came here today to join us in quantum photonics. And by the way, Ujwal, please come and visit us and greet us tomorrow evening if you're awake, because it's the first anniversary of quantum photonics and we're having a small ceremony. We will be.
Okay.
Yeah, if you are singing or playing an instrument or you wanted to read your poetry, please share it with us on stage. Because I know that probably in the near future you will become one of our regular moderators here in Quantum Photonics. Yeah. So I'll just ping some more people in. Please have some conversation with Abhis.
So hi, so it's 4 a.m. here in the morning. So I was afraid that if I will sleep, I'll not wake up. So I haven't slept.
Oh, terribly sorry about that. I know that you had a session, what was it, like probably 2 weeks ago, if I'm not mistaken.
Yeah.
Or even more than that. But yeah, so I missed it, and I think like it was too early for me, and I would probably be at work anyway. It was a Monday, I think. So yeah, that's why like I missed the session. I did listen to the replay, and I've gone through some of, the paper, if not thoroughly as I wanted to, but yeah, I'm really looking forward to it, and thank you so much for being here. I know it's not an easy thing to do to stay up all night. Okay. Yeah.
My pleasure.
Yeah, likewise.
Yeah, Abyss, actually, last time I pinned up only the popular article, but now I pinned the paper that is here. So like in the past 2 to 3 weeks, the paper of Ujwal has been all over the media because, yeah, it's something that's a first that they have done, although they had previously done brain-computer interfaces. So in a few minutes, I will introduce you, maybe in less than 1 minute, Ujwal. So, yeah, Ujwal Chaudhary has been our guest before, and he came in at the opposite time zone because he's based in Germany. So I would like to give him a short introduction. So Ujwal is a scientist turned social entrepreneur, and during the 8 years that he spent in the academia and industry after his PhD, he developed different kinds of brain-computer interfaces for communications in individuals with locked-in syndrome and complete locked-in syndrome. And he and his team had pushed the limits of brain-computer interface for the first time in history and enabled the complete sentence formation by someone on a complete locked-in syndrome. And yeah, that was his paper, which was recently published in Nature. So moving forward, he is establishing a nonprofit organization called ALS Voice to provide customized means of communication and solutions to individuals with communication deficits worldwide. Many people worldwide are in desperate need of means to help them communicate. So ALS Voice aims to provide them with a voice, empower them, improve their quality of life. So actually, it's like a nonprofit organization, just like some kind of startup. So they are now working to look for donors and supporters to help people who cannot find their voice. So please check out later the website of Ujwal. So yeah, I would just like to say briefly about the article that was all over the papers last 3 weeks ago, which was headlined. The paper is on the top of the room. Then the popular article says that brain implant allows completely paralyzed patient to communicate. So a paralyzed man with no voluntary control of his muscles, including his eyes, had regained the ability to communicate in full sentences through a brain implant done by the group of Ujwal. So after months of practice with a brain implant, the man was able to compose a full sentence. I love my cool son. So the findings are detailed at the top of the page in this Nature Communications publication. So yeah, and I have talked to Ujwal that at this point, of course, those who are interested in the paper, yeah, he can also speak about the paper, and he can also speak about the brain-computer interface experiences that he had in general. So yeah, without further ado, I give the microphone to our honored guest, Ujwal Chaudhary.
Thank you for your kind introduction. So I thought I will do it this way. I'll just talk a brief about the basics of BCI, and then I'm open to questions after that, so that we can have an open discussion and question and answer session. So just a brief overview of what is brain-computer interface. So brain-computer interface uses brain activity by bypassing the paralyzed motor system to control external computer or external electronic or mechanical device. So let's say that someone who is paralyzed and cannot use their external extremities like hand and limb to walk or to talk or to control the external device, then this kind of system can enable them to control their external environment just using the brain signal. So the BCI can be subdivided into two major types, invasive and non-invasive. So invasive basically mean we are acquiring the signal from inside the brain. And non-invasive means we are acquiring signal from the top of the scalp. So irrespective of the kind of the signal we acquire, the acquired signals are processed, filtered, and decoded using artificial intelligence algorithm, and the output is being fed back to the user, which allows them to modulate their brain activity. So an invasive BCI measure neural activity directly from the brain, and that is of course after surgical intervention. An invasive BCI approach may involve implantation of microelectrode grid by surgical process or a thin sheet of electrode which sits on the top of the cortex. So we acquire the brain signal, then this brain signal is, like I said, processed, filtered, and decoded using artificial intelligence algorithm to generate control signal to either enable communication using computer or to control an external robotic arm. Now moving on to a non-invasive BCI. So the non-invasive BCI basically is based on electroencephalography, which acquires the summed activity of neurons lying inside the cortex from the top of the scalp. Recently, there has been other kind of techniques, namely near-infrared spectroscopy. So electroencephalography or EEG. So it is based on three different kind of signal called slow cortical potential, sensory motor rhythm, and P300. So these signals are acquired, and like I said in the very beginning, the signals are processed, filtered, classified to generate control signal to control external devices. Now, in the case of locked-in state, several kinds of BCIs have been developed. Both invasive, non-invasive kind of BCI has been developed, which enabled communication with someone in locked-in state. So, just for the people who are listening and are not aware of what is the difference between locked-in and complete locked-in state. So, when a patient can use their eye for communication with the rest of the body in a paralyzed state, they are said to be in a locked-in state. In the case of ALS, amyotrophic lateral sclerosis, in the case of ALS, most individuals' disease progresses until they lose control of the eye muscle. Then they are said to be in a completely locked-in state. And so far, all the attempt to enable communication with someone in a complete locked-in state did not give a good result. Even our past attempt to enable communication with someone in complete locked-in state was based on non-invasive BCI, that is, the acquired signal from the top of the scalp, only resulted in very limited classification of yes and no communication. The classification accuracy was low, the signal was slow. So we knew that this cannot be used to enable communication. By communication, I mean to say sentence formation, real fluent communication with someone in complete locked-in state. So with that goal in mind, we are looking for different kind of technology which can enable communication with someone in this particular state. Then we after research and talking with different groups, we decided to use this latest technology, which is our invasive BCI, and we implanted one of our patient who at that time when we started with him before implantation was using our non-invasive BCI for communication. But as you know, in the case of ALS, as the disease progresses, they cannot use the non-invasive BCI, and this is what happened with him as well. So when we implanted him, he had lost his ability to use the non-invasive BCI, and 3 months after implantation, he started using the invasive system, with which we implanted him. So at this point, if you have question, so let's talk and ask question, and let's have an open discussion.
Yeah, thank you so much, Ujwal. I give the privilege to Abyss now because he missed asking you questions last time. So later on, those who would like to ask questions, you may raise your hand and come up the stage. So Abyss, I give the mic to you now.
Oh, thanks, Cecile. Yeah, I guess so far it's clear. So I do have more technical questions, but I'm kind of saving them till we go to the nitty gritty part of at least the sort of the most interesting part of the paper. So, Ujwal, you're doing Ujwal, you're doing good. I'll let the other people on in the audience to ask questions for now, but yeah, I can probably delay the technical questions for later. That's okay.
Okay, let's see if people have question. If not, then please feel free to ask question.
Yeah, I would just like to ask you, Ujwal, in trying to condition this patient who was in the total locked-in syndrome, where you did a brain implant, how were you able to train him? You had to train him to be able to communicate. Can you tell us a little bit more about how you trained this patient to communicate?
Yeah, definitely. So initially, we instructed him to imagine or attempt different kind of motor movement, like move your hand, move your feet, move your head. This was all attempt. As we know, he cannot do that. But instruction was that you have to try out to imagine this kind of movement. So we did this for almost 75 days. Although we were able to record signal response to these tasks, but it was not consistent enough to design decoder for communication. So at that point, we changed our strategy. We changed our strategy to neurofeedback, where the patient received the feedback of his activity in real time. And the task of the patient was to modulate the frequency of the sound wave using his neural activity. So what happens in a neurofeedback design? What happened that every block started with a target tone, either of a high frequency like bah, or a low frequency bah. And this target of high frequency or low frequency was then followed by a sound wave that the patient had to modulate using his brain activity. That is, increase or decrease the frequency of the sound wave to match to the target tone. And so initially, when we started, we told him that you can use any strategy of your choice, but whatever strategy you are using, please do it consistently and try to match to the target tone. Immediately, on second day, he was able to match to the target tone. So once the patient was able to do this task with up to 90% accuracy, we moved on to a speller task. So the main difference between the speller and the feedback task, well, both of them are feedback. I'm only using different name to differentiate between these two tasks. In the speller task, instead of a target tone, the color of the alphabet's sector and each character were played using a sound system. So remember, during a training block, there was a target tone, and then it was followed by a sound wave. But now, during the speller block, the target tone were replaced by the alphabet and the color of the alphabet sector, and then the sound wave was played. So if he had to say yes to a particular character, he increased. the frequency of the sound following the character. And if he had to say no to a character, it decreased the sound, the frequency of the sound wave following the particular character. So with this particular strategy, he said yes and no to select or not select a particular character. Then he formed words and sentences. And with this particular strategy, he formed long and complex sentences about his well-being, about his family, about his desire, and many, many things.
Yeah, so I'm just curious, how were you able to know that the training is effective? I mean, during the initial stage of your training.
Yes. So now there's a target tone. Then he is increasing or decreasing. So if he's increasing, you will hear the tone like, so okay, target tone. Now, following the target tone, there's sine wave. Now, what he has to do, he has to increase the frequency. So what he will do? So you see, he increased the sound, which matched the target tone. And as soon as it matched with the target tone, he received an award, like a ka-ching, saying that you have received your target. So with this particular strategy where he was able to hear that he's increasing, and when he matched it, he got a feedback saying that you matched it. So this is how we knew, and he knew that he is doing the task. Of course, we repeated it for several times. Every block consisted of 20 target, 10 of high frequency, 10 of low frequency, presented in random order, and we repeated it for several times. Only when we had classification accuracy of more than 90 to 95%, we moved further to speller session.
Yeah, thank you. I think Abyss has a question.
Yeah, quick question, Ujwal. Is this done in collaboration with BrainGate? Because I see John Donahue as one of the co-authors.
At that time, when the project was sanctioned and we got the money, John was the director of the WIS Center. At that time, he was also in the WIS Center, and he actually sanctioned the project, because of which we were able to perform this study. So we are not related with the BrainGate. So it's different from the BrainGate, to answer your question short.
Gotcha. Thanks. Yeah, if you want to continue that, that's okay, I suppose. I guess we probably would have people raising their hands to ask questions at this time. Okay, we do have Amy here.
Yeah, also for the reference of everyone who just came in, the article, the popular article, and also the paper, as here on the top, is also in my Twitter. So yeah, if you want to look at references, because we could only pin up on one link in Clubhouse, it's in my Twitter account. So please check it out if you need more references. So yeah, we see two people on stage here, Amy and Darcel. So yeah, Amy, if you would like to ask a question or make a comment first, the mic is yours.
I'm sorry that I came late in the room, but it's a very interesting topic. So I'm going to read for a minute before I post my questions, but I do have questions. Thank you.
Yeah, no problem. Yeah, we'll circle back to you. So, Darcel, would you have a comment?
I do have a question. Thank you for bringing me up, Cecile. And you all. My question is that you can train the patient in a way to where, you study the brain waves or the EKG or the, whatever the brain does to communicate, to give you that information, basic alphabet. Does that, are you also capable of, when those person who has ALS or whatever that is, I guess my question is, can that extend to if a person has to urinate or if they have to have a bowel movement? Are they able to, people who can't control that or have no control, does that work over the organ control, so to speak, if that makes sense?
So in the case of ALS, what happens is that these people are on artificial ventilation. They do have control over their bowel movement. But to answer your question in short, no, the BCI currently is not at a place where it can influence the organ function. Other than, just to answer your question very short.
Okay, great. And my next question is that through the apparatus or device or system that you use for the patient to communicate with his body, is there a way to, if two people have this same issue, can there be a shared thought process or shared information? I guess kind of like, and I don't know if that's like Neuralink or not, but I guess what I'm getting at is that is that a way to also an optional way for communication?
Sure. There is actually a study from 2016 where they enabled communication between two healthy individuals. Two healthy volunteers on two different sides of computer on two different continents, where they were able to communicate using just the brain signal. But it has not been attempted in patients, and particularly with patients in such state, because this patient is the first one in the world to have such a means of communication. But when we move forward and we provide such a means of communication to several patients, then this kind of possibility can arise.
Wow, congratulations. Thank you. That's all my questions. Thanks.
My pleasure.
Now we go to Alfonso if you have a question. Or Abis, okay, go ahead.
Thank you, Cecile, Ujwal, Abis. I just came in a few minutes ago, but I didn't have a question. Now I have one. I just wanted to suggest, Cecile, if you want to pin more than one link, what I do in my rooms, I use Linktree, and you can activate whatever links you want people to see. So you click on that and you have many links at the same time. That was just a quick suggestion that I had. And then the question that came up as I was listening was, do you have people who perhaps have the means or are into transhumanism who don't necessarily have an impediment that seek a brain implant or an interface in order to enhance their normal cognitive ability or something like that?
Okay. Okay. So I'll tell you my philosophy to answer this question. I see brain implant as the last resort. There are several technologies available before brain implant. Even non-invasive BCI means a system which uses signal from the top of the body, the top of the scalp, can enable communication, but of course they have their own limitation. We only implanted this patient because there were no other means of communication possible and available. If we had something, then we would have never implanted him. Because as you know, implant comes with its own risk. There is risk, for sure there is risk. But we always have to take into account the risk and its benefit. And for this particular patient, the benefit outweighed the risk. Now, if some healthy individual who has no disability just want to have it for fun, I would not recommend it.
Oh, thank you, Ujwal. Appreciate that.
So, Ujwal, I guess it's probably time to probably get a little more technical. So I guess you've seen the Neuralink kind of initiative and other research areas which kind of heavily focus on recording from multiple units as opposed to improving the quality of recording. So which side do you think is going to benefit the most? Because I haven't been able to find what kind of electrode you used for this experiment, but I assume that it's probably a Utah array that's is it? Okay. So it's like 100 recording electrodes.
Yeah.
Oh, was that?
128. So we used
right. Right. So I guess my question is that basically even from 128 they can get a good amount of discrimination between different units, and from that you can design your BCI. But recently the movement have been going for recording from multiple units by having multiple implants. So I guess it's just an opinion question for you. Which paradigm do you think is going to fare well in the realm of BCI?
I really think that if we get the possibility to record from several sites, then the chances of success are even higher. Because, for example, let's say that if we use just one grid, then we are restricted to that one particular region of brain. What if, this is just big if, what if we implanted in that particular region and that region is not responding? Then the whole implant is a failure. But let's say that we use several sites and implant. Let's say that even if one of the sites is not working, we still get a signal from the other site. The chances of success is higher there. So I would really pitch for multiple sites.
Gotcha. But I thought the common procedure of doing BCI, or at least before doing implants, was to record the bold response by doing fMRI, and we request the patient by giving them some kind of mental task that would be replicated using a BCI system. So does that wouldn't that mean that you can actually essentially ask the patient to localize where you can record the signal, vis-a-vis that you don't probably need multiple implants?
Definitely, this is how it is done. But once we implant the patient, then since these systems are not MR compatible, we cannot put them in the scanner. Let's say after implantation, and because of the neurodegenerative nature of these disorders, let's say that this is all big if, this is all hypothesis. I'm just talking hypothetically, putting my argument for multiple sites. So let's say that you implanted based on localization, everything worked fine. Now, because of the neurodegenerative nature of the disorder, that particular site is affected. Then it's all gone. But if we had implanted at several sites, and let's say that only one side is affected, other are still working, then we still have chance. So that is all my argument. I'm just thinking of terminal cases, not for people where there's no neurodegeneration. For example, in a stroke, there is no neurodegeneration. People have stroke and that's it. It stops. So there you localize, you put in, no problem. But in case of ALS, MS, another kind of disorder where it progresses and you never know which brain region will be affected. Of course, we know the progression. In this case, I would really pitch for multiple sites. And did I Did I make myself clear? Does it make sense?
Very much so. Because I didn't take into account the fact that this is a neurodegenerative disease, and you need to capture as many activity as you can. Because, like you said, certain part of the brain can just simply disappear, because there's like this race against time for that particular part of the area not to area of the brain not to degenerate, which raises the other question: why M1 though? Like, why not go for BRCA or Wernicke areas, which are usually associated with speech synthesis?
Yeah, and the answer to this question is it was based on practical decision, because most of the implant, as you know, was on M1, SMA, and premotor area, and this had shown promise and great result, and that's why we implanted him based on past data.
Gotcha, makes sense. Amy, I saw you on Flash.
Yeah, I was going to ask the same. I was going to ask the same question you asked, but I'm trying to read more data so I can do a compelling question, because I did have a patient with ALS like 25 years ago. I can't remember now. And I've seen the progression, and it really broke my heart when one day the family told me he passed away. So I just, wanted to tie up the things that I experienced to what you are talking about, and then I'll post my questions later on.
Awesome. Great. So my next question was about the signal processing. So I remember what was it, like a group at Stanford, well, that was like probably back in 2008, they actually had success by using Kalman filters to predict mouse position for a non-human primate implant. And I believe that the first patient for BrainGate actually also had had implants, and they implemented ridge regression to essentially predict, or at least to move a robotic arm. So I'm curious, like, what kind of filters did you use from after recording your units so that you could encode those to like the typical, the sequence of words?
Yeah. So do you know that there's a recent paper which came out last year where they decoded the imagined speech, right? Did you get a chance to look at that paper?
No, I haven't.
Actually, this is a latest paper which came out last year where the patient they implanted, and he was imagining what he wanted to write, and then they decoded what he was imagining. So far, all the implant, and for example, in the BrainGate trial, people have done fantastic thing. They are typing at incredible speed. They are moving the robotic arm, even the wheelchair. This is incredible. But all these patients, if you see, they can still move most part of their body. They can see. So when you are able to see the BCI, it becomes quite easy to design a BCI. But imagine a case where you have just one sense, and that is you can only hear. You cannot see. Then designing a BCI is a very challenging task. Of course, when we started, we tried to use everything which was done before us, like motor imagery, motor attempt, using different kind of filters which people have used. But again, we were racing against time, because our goal was not to design something, fantastic, something very cool, but our primary goal was that we have to enable communication with him. That was our primary goal. So after our initial failure of using all this previous method, we then just stuck to the very simple one, neurofeedback, where he was getting the feedback of his activity in real time. So now in terms of signal processing, what was done? So as you know, this neural signal processor acquires signal at a rate of 30 kilohertz. So this 30 kilohertz signal was downsampled to 20 hertz. Then the signals from different units were averaged, and the averaged signals were thresholded. So let's say if they were averaged and normalized, yes, averaged and normalized. So after normalizing, two thresholds were used. One from 0 to 0.25, then other from 0.75 to 1. So anything below 0.25 was no, and anything above 0.75 was yes. So this was a very basic signal processing we used to determine the modulation of sound tone just by simple thresholding.
Gotcha. So was there a word predictor that was involved to make the task of prediction much easier?
Yeah.
Okay.
Definitely. So what we did, this we implemented on and off. So what was done, that first the patient selected character, he formed words, sentences. Based on that, we created a dictionary of his selection. So after a dictionary was formed, so as you know, similarly, like any other dictionary, let's say he selected A and C based upon what was his frequent words formed using A and C. Words were proposed. You want to select act or action. Then he just said yes and no, and the program completed the word. So of course we tried to implement that part.
Yeah, that actually makes things a lot more better. I was attending a different presentation by a different group where they were actually managed to do a BCI, a semi-invasive BCI using ECOG on a visual cortex and the occipital lobe, and they use some kind of word-to-vec kind of encoding to represent the images so that a person can actually recreate that image in their mind to activate the BCI. So I'm just curious, like, did you try to use different kinds of encoding that would, of course, in this case it will be tonal encoding, I guess, that will make representation much easier. You did talk about that before when you were when you're answering Cecile's question, but I guess my question is more geared towards to like something which can be processed using machine learning so that it can have a predictive pattern by just simply playing around those tones.
So it has not been implemented, but to answer your question, so let's say that so patient is lying, his eyes are closed, but he knows that what are the things he's going to select to form a sentence. And when I was performing the study, and from the observation, it was very clear that he already knew what, of course, he knew what is going to come next. And for him, the selection was sometimes very instantaneous. So let's say, with this background, let's say that patient has formed a sentence, I'm happy, which he actually did. I'm happy. Then for I'm happy, we have a neural representation. And so what should we do next? We then instruct the patient to spell I, then in another session, spell M, and third session, spell happy. Then now we have a template of I'm happy, and we have a template of I am happy. Then you try to match the template and see that are you able to predict? So, but of course we did not implement this kind of thing, but it can be implemented in future when we do a similar thing with other patients. So to answer your question, no, we did not do it, but we do want to do it in the future, using the idea which I just said.
Yeah, that's really amazing. And it's like this is probably like my last question for now, because I don't know if there are people that still want to ask questions. That'll be if you actually manage to, or at least like to think of multimodal kind of recording in a way that if you have an invasive technique, and you did mention about P300 early in the discussion. Early when you were talking about non-invasive BCIs. So I'm just wondering if the degenerative disease itself actually prohibited you from doing multimodal kind of collection where you can apply EEG at the same time with invasive kind of recording to make predictions more faster.
Yeah. So my time with this patient after implantation was cut short because of many reasons. But there were some studies which I had proposed. One of them was, so if you read the paper, then there are good days, there are bad days. Then the question arises, why some days are good and why some days are bad? So to answer this question, I proposed that what we should do is that acquire his EEG, acquire his sleep EEG, and then try to come up with a kind of a biomarker saying whether that was a bad day, a bad night, or a good night. And my hypothesis is that the sleep of patient affects his performance. Okay, this was one thing. The second was that before the start of every session, we always recorded a resting state baseline period of 10 minutes. So one hypothesis I formulated was that from the resting state, can we determine a kind of a marker which will tell us that the session today will be a bad session or a good session? This was the second question. The third one was, while we are recording the neural firing during the spelling session, let's also record EEG and try to find a neural correlate of his performance from the EEG signal. So these were the questions I wanted to ask, but my time was cut short. And I couldn't ask all these questions. But of course, these are very interesting questions, and I plan to ask all these questions when we implant other patients through ALS voice.
Yeah, awesome. And I guess implementing EEG or having EEG along with brain, such an invasive recording would be ideal, and it's very easy to convolve as well because you don't have that level of time delay with other modalities. Thank you so much, Ujwal. So if there is anybody that's willing to ask questions, please do raise your hand.
I want to ask, how do you pronounce your name? Ujwal?
Ujwal, yeah.
Ujwal, okay. How long was the lifespan of the patient after you have implanted the electrodes?
So as far as I know, the patient is still alive. We implanted him in 2019, and this is 2022. So I was personally involved with the study until the end of 2020, and but as far as I know, the patient is alive and is still doing fine.
That is a great experiment then. And going back, I know you said that putting the electrodes are your last resort. And I just went back and read up on ALS, which I was really intrigued by it 25 years ago. Not much research was done on it. I know it's a rare disease, and it's a fatal disease also. And I just wanted to know if anybody out there has already experimented on how to regenerate the motor neuron. The nerve. The nerve that were damaged. Have anybody experimented on that before it becomes really a bad, debilitating disease?
There are different groups working on it, but we do not have any solution so far. there are groups working on a neuron regeneration, even on trying to procrastinate the progression of the disorder. But we didn't, but nothing new so far.
So there was no experiment on implanting another nerve or anything like that after it degenerates?
No. What you mean to say is stimulation, right?
That too, but since surgically, I don't know if anybody had tried to attach a new nerve. No?
No. Okay. So as far as I know, no.
I was just wondering. Thank you for your
And these are all good ideas, you know. No ideas are bad idea because only when we think we can achieve, right?
Well, yeah, in thinking about that, it's the nervous system that is, dying, and it's, the ones that's attached to the muscle. I'm thinking that somebody would have thought to implant one that would help it, regrow or whatever, if they have found out how to do that.
The problem is that it is not just one neuron. You have to, this is all we are just discussing, this is all hypothetical. It has nothing to do with hard science. So what you're basically saying is that you want to replace the complete motor neuron. Replacing one neuron cell, I can't say one, few neurons, and is very different from replacing the complete motor neuron system. And our science has not progressed so far, and we are still scientists are still debating about generation of a single neuron. So we are still very far away from there.
Yeah, Ujwal, there's a recent study which came out, and I'm inviting the researcher about this in the concept that we have about neurons firing individually to reach their peak. There is a recent study which came out which likens the brain to what is being likened in physics as, that of a particle and that of a wave, because they came up with the wave interactions which try to collide with each other in a recent paper. And I'm very curious about that because, there are new studies that are coming out that tries to create new science, and I thought maybe it could be contributory to whatever kind of design that you would be making in the future as you proceed with your philanthropic work about ALS voice. So maybe later on I will ask you to tell us more about it after other people have asked their questions.
Okay.
Yeah, and also I would like to weigh into Amy's question. Joel, I don't know if you've seen this research itself from University of Minnesota, where they were able to do brain implant on a person that has cervical spine injury, but they were able to do implant and activate the musculature using some device to that would correlate with the person's intention to move their arms. So they're basically circumventing the cervical injury entirely to essentially enable the person to regain their ability to grasp things. That's one thing that I thought of. The other one is there is a study from University of Michigan where they were able to graft a muscle tissue on neurons, and this is widely done on prosthetics, but the idea is to boost the signal of neurons right after a person has been amputated, because recording from peripheral neurons is incredibly difficult. So by grafting these muscle tissue, it would amplify the signal by 1,000-fold. That can be picked up by an external device for prosthesis. And the last one is the guest that we had here, Miguel Nicolelis. In fact, one of his demonstrations to enable non-invasive BCI on a person with cervical spine, he later reported that that patient was able to feel some of, or at least like gain sensation in his hands. So in a way, by kind of enabling brain-computer interface, that there's a chance that spinal injuries can be kind of healed in a way, for lack of a better word. So yeah, these are some of the few things that did come to my mind as Amy was asking the question, and you, Cecile, and Ujwal were addressing, or at least like opining their answers.
Because I was thinking, if it's just the peripheral nervous system that really gets attacked with whatever disease that is, attaching a new nerve on that muscle would probably help. That's just a thought.
So what we're talking about right now, it's called functional electrical stimulation. So what happens here is that so we are all thinking the same. Well, you know what is functional electrical stimulation. I don't have to talk about it then.
Oh, but the audience might not, so please do.
So basically, in functional electrical stimulation, you stimulate a particular part of your musculature, and you can basically stimulate that using your brain activity. In a functional electrical stimulator-based BCI, what happens, you do the same thing. You either imagine a movement or you attempt a movement to do certain, either turn on or off the stimulator. Now about the research of Nicolelis, the research work is amazing. They have designed an exoskeleton system, and this exoskeleton system has inbuilt electrical stimulator along with EEG and EMG sensors. EEG is electroencephalography, EMG is electromyography. And these sensors are there. So now if the patient or the person wants to stand up or even walk with this exoskeleton, they have to imagine. After imagining, it stimulates that particular musculature, and the patient just walk. And this is just incredible what they have achieved and are doing. And I did read about this recent paper where a person with injury in the vertebrae was just able to walk after this stimulation. These are just incredible development.
Okay, great. Real quick, my understanding so far, I come from a nephrology background and I do some machine learning. What do you think, Joel, about all the data that's coming out of the brain? I'm talking about EEG. So far, we can interpret really well due to the good diagnostic and therapeutic results. An ECG, electrocardiograph, or EMG, a muscle graph. But the EEG is so complicated, and so far we have so much information we can even interpret the right way. Even with the sleep analysis, a lot of people just look at the data coming out, have no clue. What do you think?
In our lab in past, we did several sleep study with healthy participant and even with ALS patients in different stages. You are absolutely right that EEG is a quite complicated and as well as noisy signal. But if you process the signal in a certain way and follow the standard established in the field, because as you know, EEG by itself is quite old, and the first time it was recorded was in 1928. So it's going to be 100 years now, and this 100 years, close to 100 years, scientists and researchers, they have developed very good signal processing pipeline and techniques.
Even with the fMRI, still we need a dilemma.
Yeah, fMRI is relatively new, and in fMRI, it's all dependent on what kind of canonical wave you are using right before when you start processing a signal, and it's very dependent on your Z value. You change your Z value, the brain activation changes completely. So fMRI is completely different as compared to EEG. In EEG, we get the electrical activity of the brain, you process it, and after if you do your frequency decomposition, depending upon the different band of the frequency which correspond to different state of the brain, we can actually very reliably classify the sleep stage of the healthy human being or even of the patients. And EEG has been actually reliably used to enable communication, even to control exoskeleton in patients and in healthy individuals.
Yes, I totally understand. We can have like a motor function through a peripheral nerve, like brachial plexus, all these complicated nerves. I'm talking about the level of voluntary cerebral cortex. It's still a mess. As a human race, we have no clue.
Yes, agreed. Agreed. No doubt about that.
Even with sleep study, if you're gonna look at the key spindles or the beta wave or the REM or whatever, I don't believe Elon Musk will be able to have the chip to treat epilepsy, depression. I don't think we're there yet. I don't believe so.
Today we are not there. Maybe in the coming few years, maybe we might be there. Because it is not just one company. There are several very innovative neurotechnology companies, and they are developing different kinds of electrode to cure different kind of disorder like epilepsy, tinnitus, and all.
No, it's not about the electrode technology. You have like the new electrodes like 1.008. I got that. But the point is, we don't even know how the brain centers interact together, like amygdala versus
yes.
We don't know how
that is a completely different story.
It's a different story. It's like this is
right.
Yeah. I don't think not even the next 20 years, because being a physician, I'm very aware that human race is way beyond this. We have to develop new techniques to study the whole brain centers and how they talk to each other, how they communicate. We don't know much about that yet.
Yeah, that is true. I agree with you on that.
If no more questions, I'll ask you. This is one of my favorite subjects. Are you familiar with transcranial therapy, transcranial magnetic stimulation for depression?
Yeah, TMS, yes.
Yes, what do you think, the TMS, the transcranial? Okay.
And I was once, I wanted to try, because I always did study, and I saw the responsive participant when you click on the motor cortex and the hand is moving. So I just wanted to experience it. And then I was below the TMS, and then there was click on my motor cortex, and my hand started moving by itself. I had no control on it.
Yeah, I noticed that. I read about that. Yeah. Correct.
So regarding the depression treatment, you know very well that depression has to do with the dopamine channel in our brain, and one of the region where the largest receptors and center of the dopamine channel is the DLPFC, that is dorsolateral prefrontal cortex. There are several studies coming through where they show that if you stimulate the DLPFC, then it has some kind of effect on depression. But what is its long-term effect, we still have to see.
It's empirical. It's almost a new ECT, extracorporeal shock therapy, when they used to electrocute patients in old days by the ECT.
Yes, yes.
Nobody have any idea. And even I did some research, and when you lose control of hands, the only answer I got from a couple of friends, because I'm very interested in the whole subject, I got a bunch of my friends doing substance abuse and psychiatry and depression, and they're experts in New York. They told me like there's a stimulation to the area nearby. This way you lose control of the hand, and it would contract without you can control it. But the response rate for the TMS is not really good to depression versus Spravato. But this is two different subjects. But
yes.
Mm-hmm. Nice.
Yeah, and I also wanted to mention that there are deep brain stimulation techniques that not just alleviate conditions of Parkinson's, but also treat severe depressions. I don't exactly remember which area that they're targeting, but yeah, that will be an interesting thing to take. But again, I'm also cautious about some of the hype which has been made by Elon Musk and others, because these kind of brain pathologies need to be accessed, or at least like they're sort of deep within the brain in their subcortical structures. So I think that will be incredibly difficult to at least stimulate or at least like reach out to these areas without doing some kind of highly invasive technique or highly invasive method.
Yeah, deep brain stimulation has long been used and tried, but it's basically like surgical anatomy. The neurosurgeon go in there, put the electrode, click, short circuit, see what's going to happen. And that's basically what we're doing. Elon Musk's so much hype, and deep brain stimulation is working actually, and even vagus nerve stimulation. It's FDA approved for resistant depression as a clinician. So far, the research in this area is hit and is by trial and error. Like just hit, you put the deep electrode and the short circuit, put some wave action potential, and see what's going to happen. That's what we have so far. We don't have precise maps, surgical maps yet.
We welcome Shara, who just came in. So, yeah, Ujwal, I would just like to ask you, because I understand, of course, the patient that is referred to in the article above, they said that there is some scar tissue which has already developed on the implant, and the fidelity of the signal processing is not the same anymore. However, it is still doing its job, and I think they will just keep there has been no change in the implant, right, since the time that you had installed it in the patient?
I know only of the status until December 2020, and after that I have not been touched, or I'm not a part of this project, so I don't know actually. So
anyway, since you had mentioned that you are turning social entrepreneur, and you are trying to establish ALS Voice, which is a nonprofit. Can you tell us a little more about it? Why are you doing this, and what's the mission statement of ALS Voice, and what is your plan about that moving forward?
Yeah. So during my time in academia, we were always limited by funds, and we always had a waiting list of so many patients, but unfortunately we never got a chance to work with them because of the limited fund. And when you are a part of university, you can only do, let's say, when you write a grant on n equal to 5 or 4, and then you are just bound by that. So moving forward, I thought that no, this is not the way. If I really want to bring this technology to people who needs it, then having a company is the right way. But then I was thinking that forming a company will not be a right way, because there are people who cannot afford such kind of communication technology, but they really need it. So we decided to go for a non-profit model so that we can raise money for them through different means, through donation, through health foundation, through private donors, or even patient by themselves can raise money. Since it's a non-profit, they can work with us. We can raise the money. We can provide them the communication service. So because of that, we adopted the non-profit model. And moving forward, we are actually getting quite a few inquiry from people all over the world. And then the problem remains the same. How can we fund it? People want this technology. They want means of communication. They are desperate. They have no voice, but they want this. And we want to provide them this kind of technology. And for that, if people are listening and if my words fall on the right ear, then we are looking for potential donor and supporter, and their help can really help us provide means of communication to this patient who really needs it.
Yeah, I understand you are just starting it now, right, Ujwal?
Yeah. So we incorporated it in December, and now we have formalized all the administrative process. We are now developing our software. We're developing the software in such a way so that we can make it open source. The goal is that anybody can use it. So in a few months, we will make our software live, make it open so that people can use it.
Yeah, I remember when talking to Miguel Nicolelis, of course, he's with the Duke University and he's chairman emeritus. And he was wondering whether he will go back to the academia, because he said, of course, when you have grants or other means of financing as given by other sponsors, you are bound to whatever specifications that they have about the study. So he was considering to look to take his research and also to go philanthropic and build up, blue sky science, so that his research will not only be limited to what is being specified, and that in a very big way he would be able to help people who have problems about their brain, and especially starting in underdeveloped countries. So I think he hasn't really started so much on this, because he came back to Brazil and he is working on some COVID projects. So I think he has the same outlook, having the same kind of experience, maybe in an academic setting that you had as regards to your research in brain-computer interface. So I would just like to share that with you, that I think, of course, maybe the outlook that you have as of this time, maybe it's good, and it's very sincere, to really be helping more people. So I hope you get good support in your ALS voice.
Yes. Thank you so much. Thank you for your kind words.
Yeah, so I'm also concerned, especially in academia, when you're trying to embark on such a grand project, it's not just the budget or the funding that comes into that is one of the typical constraints. It's also the IRB. So how is it like when you go public? Is there some kind of institution that you want to that you kind of hold into, and how does it make life a little easier or difficult in that regard?
Life becomes even more difficult. I'll tell you why.
That's what I thought.
Because if you're a part of university, you know the process, you know the where to apply for IRB, you get the approval. But once you go private and you are not a part of the ecosystem, then you have to look for the local medical authority which will approve the complete process. But since since the last 8 years, we did several kind of study using non-invasive and invasive BCI. And for invasive BCI, actually, we got the approval from BfArM, which is the medical equivalent of FDA in Germany. We got the approval from them. It had nothing to do with the university. So we know the route now. We know the pathway, which path to follow to get the approval to do this kind of study. It is a difficult path, but it is achievable. We can achieve it, yes.
Got it. Amy, I think you had a question.
Yeah, I just have a suggestion for you, Ujwal. If you open your crowdfunding to the Web3 world, meaning to say you can accept crypto for donations, you'll get a lot more response. There's actually a BCI conference head in Amsterdam right now, which is a conglomerate of scientists trying to get into the same situation you have, trying to raise funds for their research and all that. So, and I applaud you for pushing through. I really am proud of you. Thank you for doing that.
Thank you. I will look into what you just said. I'll try to find it out. Thank you.
Can I ask a question?
Yes, please.
Yeah, thank you. So here's the thing. I'm very fascinated with the idea, and I think this is like our last frontier for the human race. We did very good with the cardiology, nephrology, kidney, stem cell research. We cured the first patient of diabetes, Brian, last year. This is a great accomplishment. Right now, I'm just my dreams and my hopes, and I'm banking on AI, like building the machine learning to emulate the brain centers, because I know so far we don't know much in medicine about how different centers in the brain can communicate together, and we need a different approach to understand how this works. It was very easy for us to decipher the stomach at the pacemaker in the heart, how it works, how they communicate. Even the BART, when you send this electric stimuli in the nerve, it goes to the motor end plate and releases acetylcholine. And then when you have all the things from the basic pharmacology, SSRIs, slow serotonin reuptake inhibitors, and all the pharmacology. The thing with the brain is a little bit tricky. You have electric stimuli which release chemicals and hormones, which we don't know much about, and the centers are standalones, but they communicate in a way very adaptive. It changed, like the channels we know years ago, it keep changing, and it's different from a person to a person, a disease to a disease, the same normal human being. I think the only way we can approach this, like a fuzzy environment research, decision making in fuzzy environment. So I'm banking on machine learning and building a deep neurological networking learning models, AI. What do you guys think?
A machine emulating the function, maybe.
Yep.
Maybe, because you can do that with different electrical component, but forming connection the way the brain formed, forming the memory and experience the way the brain form those transistors, or whatever the electrical component will be in the future, should be able to self-assemble themselves. Without that, this kind of experience which brain enable us to have is not going to be feasible with just an algorithm. It has to be supported by the right hardware components, and those hardware components must be able to self-assemble themselves, like the way our neurons does.
one of the AI definitions is a learning machine can build itself. One of the good definitions of AI. I know an AI cannot develop consciousness, personality, and for reality testing, but this is more philosophy more than medicine. But
Definitely, definitely. Yeah, we can debate on it for a long time, but we keep on debating.
The central nervous system is a very complex network, so yeah, it'll probably be a very, very advanced kind of AI to be able to replicate that.
I'm not trying to replicate. I'm just trying to back and see how it works, because it's again, it's bridge not just electric connections and neurons and astroglide cells and all the cells with studies. Even the retina of the eye, you got like 10 layers of cells. If you go into it, it's just nuts. And I'm still fascinated by the brain centers, who still doesn't know much about it, how they communicate, how they change in certain diseases and personality disorders. I'm just trying to learn how to work, try to decipher it, to see what's happening. I think this is one of the tools we should use or investigate. Like when you look into cells, you get a microscope, electron microscope, you can look inside the cell. You can look into mitochondria, you can look into microorganisms. We get to not the cellular level, actually to a molecular level. You can basically look at the molecule itself, which part in the cell it is, what it's doing. And molecular genetics is awesome. We are not that good when it comes to brain. So I'm trying to figure a way to study, to figure out what's going on. That's all. Crazy ideas.
So there is a paradigm in neuroscience where if you're trying to establish the connection of different types of neurons, that you can create rudimentary machine, well, you wouldn't call it machine learning, but sort of like a connectome model where you can essentially represent different neurons. So that is one way, but also I would caution that, the machine learning approach that we have is completely different from how our brain operates, and Wissam is here on stage and probably can completely elaborate on that one as well. So the fact that we do have so many advances with deep neural networks, with transformer models, does not mean that we're ready to emulate the brain, or at least try to understand it in a way. These are two completely antithetical approaches to trying to define intelligence, or at least get to intelligence.
No, I'm not going to talk about IQ because I don't want to ruin the room. This is like $1 million questions. Like you can get a Nobel Prize if you can answer these questions. I have to remember this. I think there's a developmental study talking about neurons and developing neurons. There was a study that says cab drivers in London have a certain part, I can't remember which part, in the brain, just by studying the map. I'm sure you guys know about it. Also, if you do intellectual functions, intellectual job, you will age pretty well. You will push back Alzheimer and Parkinson's if you practice a lot with brain functions. It's like the brain age game. I think I can look up the study about the London cabbies and their developmental change to the brain due to the maps.
So it's the hippocampus, actually. Always thicker. It had thicker gray matter, I think, if I'm not mistaken. So that goes to show that the brain has a simple rule: use it or lose it. So these cab drivers were instructed to memorize as many lanes as possible, so that inadvertently helped them to have a much kind of refined spatial memory compared to others who have not gone through the same rigorous process. So yeah, that's what the brain does. Essentially, if it's not used for the intended purpose, it tries to repurpose it, or at least sever the connections, because our brain is constantly evolving. It's creating and severing synapses every time. So yeah.
Yes, synapse development is very complicated. I try to understand it, and it's developmental. Yes, and there is a rewiring. Like you have the same components, same neurons, but it gets rewired in a different way every second, and it's very hard to learn the pattern. This is what I'm thinking about. Yep, you're totally right.
And the brain knows how to readapt itself whenever there's an injury or something. So, same way with when you have a stroke, sometimes it rechannels the connection and you can relearn something.
Yeah, I would just like to have a short interruption of the discussion here to announce that we are going to stream the live interview of George Church here in Quantum Photonics on April 26. It would be around lunchtime PDT and 3 p.m. EST. So we might not be able to ask George Church a question directly, but maybe we can type in some questions while we are trying to stream the podcast of our friends Misha and Xingli from MIT and Harvard to Quantum Photonics. So please try to check our schedules, and hope you can join the simulcast that we will have. So yeah, thanks. So yeah, back to our discussion here with our special guest Ujwal. Just to reset the room, yeah, Ujwal was our guest in another schedule before because he's based in Europe. So we invited him. He didn't sleep, for this evening, just to be able to accommodate our audience here who are on a different time zone. So yeah, I'm very thankful, very appreciative of what he did. And for those who also just came in, his a paper that he was involved in about the brain implant that allowed somebody who is completely paralyzed to be able to communicate in sentences was published about 3 or 4 weeks ago. And this is not the only study that he has. He had some good experience about brain-computer interfaces. So we invited him here today to tell us about his experience and his studies in brain-computer interface and brain implants, and to tell us, about his outlook on his personal projects for the future, and in general about brain-computer interface. So if you'd like to ask questions or have comments, please feel free to raise your hand and go up the stage. So we would also like to welcome Wissam if he is here right now. Thank you for joining us.
Hello, how's everyone doing?
Yeah, we missed you on the first part, but thank you for coming.
Yeah, I'll have to catch up on the replay. This is super interesting. Thanks for spending time to share your work with us.
My pleasure. Thank you.
Yeah, Abyss.
So, yeah, thanks, Cecile. So, Ujwal, I do have a question. I believe, I don't know if you experienced this, but there are some electrode failures that would contribute to misclassification when using the Utah array. Of course, that there is compensatory effect, like you can actually pick up the units from other nearby electrodes, even though one fails. So I'm just wondering, like, what is the probability of that happening in a clinical setting?
So for 1.5 years, when I was with him almost every day, consistently there were some channels where we always saw the activity, and they were always present. There were other channels which were coming and going, but there were a few channels which were always there. So yeah, this is all I can say to your question.
Yeah, so the reason why I asked is that in order to implement these kind of electrodes for a prolonged time, you need to have like that signal acquisition that increases the signal to noise ratio.
Yeah.
That's one thing. And also you need to, or at least like it's important for all electrodes to have sort of peak performance when recording. But I've seen a non-primate studies that also use Utah array. But whenever, like I said, whenever there is an electrode that's actually failing, the others actually compensate for that. So you can essentially pick up the units from that would have gone to the missing electrode, and that will be picked up by neighboring electrodes. So yeah, that's one of the reasons why I asked you. Like the sort of, I guess the question is also more geared towards the durability of the implants, given that everything has gone well and there is no edema or sort of like an infection around the implant.
So there was no infection for sure. It was all clean, and there was no complication related to the surgery, nothing. But the thing is, we do not know about the kind of neurodegeneration which might be happening in such state. So whatever we say, this is all hypothesis without any sound backing to it, about degradation of the channel, about necrosis of tissue, and things like that. We can only hypothesize why it will not work or why it is not working now.
Gotcha. And also, I guess I should probably ask this. I should have asked this earlier. Is there a plan to? I mean, you're gonna probably pursue this in your own private, as a private company, but based on the research institute that you're in, or the lab that you're working, or the lab that you have, is there sort of like a plan to replicate the same kind of success on another patient?
Yes. So now I'm full-time on this ALS voice. I'm not affiliated to any university or anything. I'm full-time on the ALS voice, and the goal is to implant more patients in such states. In Germany, and Germany is a country where people who have ALS, they have the freedom to choose artificial ventilation, and many patients actually choose artificial ventilation. And after that, they live for quite a long time, actually. So in Germany, there are quite a few patients like these. We have been contacted by a few patients. We are preparing. The first thing which we have to do is to raise fund, then get the approval, then start with the study. So we are in the process of doing this. And we really want to replicate, because there are so many questions which needs to be answered, like for how many years can such implant work? For example, in the paper which we published, this was quite slow. Can we increase the speed? Can we find the reason of bad day and good day? Can we optimize it? Can we enable, for example, when I was doing this study with this patient, there was something came to my mind, like, okay, now this patient is able to select characters to form words and sentences using his brain activity. Can he can he control an exoskeleton with his brain activity? Imagine that if we are able to enable a completely locked-in state patient to get up wearing an exoskeleton, just imagine what will happen then. We would have pushed the boundary again. And these are some things which I would actually like to pursue in the future when we implant few more patients in such states. Not only give them the ability to spell, but even the ability to just turn on the TV, close the window, open the door, turn on the music. Now, instead of asking others to turn on the music, he should do it by himself. Things like that.
Yeah, that's exactly why I asked you this. Because I was trying to allude to how you can improve upon the current success that you have and try to correct, for lack of a better word, the mistakes that you had in this first try, so that you can have more successful and more streamlined implant that you can apply to other ALS patients. But yeah, well said.
Evans, I agree with you. I agree with the choice of your word, mistake. Definitely, there were some mistakes, but we learn from our mistake, and from these mistakes, what I have learned, I know that we can make it better and faster in the future.
I do have a question on your experiment. Is that a 24/7 type of activity? Are you experiencing any muscle fatigue on the end of the patient?
In terms of muscle fatigue, I can't say anything to that because, this is a completely paralyzed patient. But I can definitely say on his mental fatigue. I did observe in the past that there were days when he spelled without any problem for 3 hours, no problem. And on some days, subsequent days, let's say that today is day 1, and today he spelled for 3 hours. Day 2, he spelled again for 3 hours. Then from day 3 and day 4, he could not spell more than an hour. So I think this points to mental fatigue. Of course, there is this fatigue factor there.
But is it 24/7? He's connected to it 24/7?
No. Okay, so I'll tell you how this is. So the electrodes, the microelectrodes, are inside the cortex. Then from the top of the scalp, there is a kind of a small protrusion, which is called a pedestal. This pedestal, when we are not recording, is covered by a small cap. Now, if we want to record and do something, or if we want him to talk, then we take this cap off, and then we connect a small kind of a connector, which is called seriplex E. On the top of this seriplex E, there is a insertion point for a mini HDMI cable. This mini HDMI cable then goes and is connected to a connector of neural signal processor, which is a big hardware which acquires the neural signal. So when we are not communicating or not acquiring, then this pedestal is covered with a cap. So it is not connected 24/7, only when we are recording something.
Okay, thank you.
And also, I guess this is sort of based on what Amy was asking. Is there a plan to go wireless? I know BrainGate actually is able to achieve this with sort of like a WLAN antenna that were kind of like triangulating these two signals. They had like multiple implants on the patient. Of course, like this patient had cervical spine injury, which means that they were quadriplegic. But yeah, so that going to be like part of the plan to go wireless entirely?
So actually, I read this paper where they showed the wireless system. If we get a chance to use it, we will definitely go for wireless. I had an inquiry from a patient actually 2 days back, an ALS patient from Spain, and he said that he would like to have this implant. I said, okay, then what is your status? Basically, we were communicating through WhatsApp, and he was typing on WhatsApp through his eyes. And I told him, see, you are doing so well with your non-invasive system. I would not recommend that you go for surgery. Only when you start losing your ability, then we can think of surgery. And then he said, then one of his questions was, is this wireless? Does it has Bluetooth? Then I told him, yes, there is a system, and this is a recent development that there is a wireless, and in future, the systems are going to be more or less wireless.
Yeah, I guess Alfonso, he's not here on stage, but he also asked you about transhumanism, and I think that that's kind of the promise that's being sold by companies like Neuralink, that such implants would be less harmless in a way, and then they can be widely applied. But there are some significant repercussions to doing invasive techniques. So this should be used as a last resort.
Definitely,
you just mentioned.
Yeah, definitely. This is what I tell everybody.
So, Ujwal, I would just like to ask your opinion about your. Well, it's hard to make a forecast, but how do you think are we going about the brain-computer interfaces that we're doing now, both the invasive and the non-invasive?
The neurotech segment, the whole segment of neurotechnology, I would say at the moment it is in limelight. It is receiving lots of investment. There are several budding companies that are coming up with great products. Investors are investing. Now we have to see how this limelight and how this money which is coming in is going to really help the patient. Because I really believe that if you are developing a brain-computer interface for playing game, then it is completely useless. Then it has no meaning for patients. The real application of brain-computer interface is to improve the quality of life of disabled people. If we are able to do that, then it brings value to the whole field of BCI. Otherwise, if people are just investing money to play games using brain waves, then it's okay. I do not have to say anything to that. But moving forward, I really believe that there are several serious companies who are working day and night to improve the quality of life of people with their products.
Thanks. So, Peace, do you have more questions or comments?
I feel like I've exhausted everything. Of course, like I should have. I did go through the paper, like I said, but not as thoroughly. But yeah, I think that my questions are really well addressed, and I know it's really late for you, and don't want to take up much of your time, and I would like to thank you for coming here and presenting your amazing work, and looking forward to continuation of this, where you will probably join us again with a brand new study. And yeah, that's all I have to say for now. Thank you.
Thank you. Actually, it is going to be 6 o'clock now in the morning, so I better go run now.
I would just like to say that, I really appreciate you for staying up. And of course, I know that this is not going to be the end of your coming here in quantum photonics. This is just a beginning because, of course, I invited you to be a commentator maybe, or to join the panels whenever we have brain discussions or BCI discussions, which we are having every week. So some of them may be the opposite of your waking zone, but at times when you are available, please feel free to be part of this quantum photonics family that we have. So thank you so much, Ujwal, for staying up for us, and we will be inviting you from time to time, and you are certainly invited to just come anytime and listen to the conversations and be on stage. So I wish you good luck, and if I encounter some opportunities to help you in your new project, I will certainly get in touch with you. I applaud you, for this very honorable mission that you have. So again, the name of your company is ALS Voice. Would you like to tell us about the website that you have now?
Yeah. So thank you so much, Cicely. So the website is ALS Voice, and I would plead all of you to have a look. And if there are patient, or if potential donor, or people who are willing to support this kind of initiative, or people who need this kind of service, if you can connect us with them, we'd be really grateful for that. So that's all I have to say.
Yeah, well, I know you're just starting on your website, so next time, please be here to tell us more when you have developed it further. So yeah, thank you so much. I cannot thank you, more. So I would just like to announce the coming room that we will have, and of course you should come back soon and not sleep again for some interrupted sleep, because I'm inviting you to our opening anniversary, which is gonna be tomorrow. There's gonna be a short program, and if you're playing some instrument or would like to read some of the poetry that you have developed recently, trying to observe brain-computer interfaces, that would be nice. Or just greet us and say hello. Yeah, you are certainly welcome. So
Definitely.
we will have that celebration tomorrow, because April 24 is the anniversary of quantum photonics. But I think before that, we will also have the room of K, which is almost every day. That's gonna be earlier. He will be talking about light. We've been talking about light and waves in the room of K, so he's talking about light as a boundary. Then after that, we will have our first anniversary celebration. And I just announced a while ago that Abyss, Abyss, I'm so glad that we're having George Church here, even just on a simulcast. And we will have an opportunity to ask questions, maybe just like at the back channel. So please check out our schedule here. It's very historical for quantum photonics. And of course, aside from George Church being hot before in the biotechnology field, he's also so much hot now because of his attempt to try to put back to life, to resurrect the Thai version of the woolly mammoth, to do intervention and help about the climate change conditions. So that's why he is again very controversial and is in the limelight, and he will be interviewed by our friends Xingwei and Misha. So please check that out. We have so many activities here on the week of our anniversary. We have meditation rooms, we have music rooms coming up, and also coming up is a major researcher in physics, especially in quantum gravity and the holographic universe, Dr. Mark Ramsdonk, who is coming here in quantum photonics as well, and also my friend James Ehrlich from Stanford University and Singularity University, whose project he's all over the papers now. His project about renewable regenerative villages is really gaining a lot of ground. Regenerative villages using machine learning to really fit the kind of environment that you have, and it's very a sustainable project. It's very interesting. And another one is, of course, my friend Shauna Panja, who is a physician, and she's also in astronautics. She will talk to us about space medicine. And I think she's also involved with the future of medicine. She's in Canada, and she's also from Singularity University. She's coming here. Actually, it's her second time because people wanted her to come back. And lastly, not lastly yet, but another one is we have a guest from CERN for whom I am trying to collate the questions now, together with Neil and also Hansen. So please check that out, and you will see quantum photonics generally on a 24/7 mode in this particular week. So this room, and be thankful that Ujwal is here. So so I tried to call Darcel here. We were trying to end on a positive note, actually. When we are about to close the room, we are trying to end on a note of hope. And if there are other political issues or other personal issues that are there, maybe someone can make a room out of that, or we can even make a room there where people know that is the topic. But as of now, it's way off topic. So I would
absolutely.
Well, I just brought you up because this guy was having the same complaint, but I do not understand where it's coming from. And it's like, for me, I think it's pretty rude to just butt in somebody's room to just say that outrightly without any warning. I don't like to entertain that in this room. So anyway, I would like to close this room soon because Ujwal has not slept yet. So Ujwal, thank you very much. Please come back again, and please join us regularly. So also,
Amy, it was a pleasure.
Thank you.
Thank you so much. I wish you all a good day, good evening, and good night.
Good night, Ujwal. I hope you are able to sleep this weekend.
Okay then. Bye-bye. It was a pleasure. Bye.
We please close the room with us, okay? So we will count down since you're here already. So Amy, thank you also, and Neil, thanks. Mike to you, Darcel, Abyss, thanks too.
Yes.
Mike to you, Darcel.
Thank you, Cecile. It's a great room, usual. Tonight, we're going to start the countdown with lucky number 7. Is everybody ready?
Ready.
7!
7.77.
Route 66.
6.
Route 66.
1/6.
5. 4. 33 and a third.
33 and a third.
Hi.
2.
2.
Cecile, Ujwal, Abyss, Amy, and Neil, you're all number 1. Call out the last number.
1.
1.
Yeah. Good night, everyone, including Ujwal, which is morning night.
Bye, everyone.
Okay then. Bye-bye.
Happy dreams.
Bye-bye.
See
It
you
was
all
a pleasure.
tomorrow.
Bye.
Bye.
Bye.